Alkaline earth metals, what are their physical properties like? They do hydrolyze quite readily when you put them into water. The hydrolysis reaction, as you'd expect, gets much more vigorous as you descend the periodic table. So this again is a redox reaction. Only this time it's a 2-electron process, whereas in the case of the alkali metals it was of course only a 1-electron process. We're interested in the chemistry of divalent ions, metal 2+ species. And that's actually incredibly significant. That's where the alkaline earth part of this comes in. Because we are dealing with metal 2+ species, we've removed 2 electrons. We have 2+ positive charge. These are small, very strongly charged species. Remember, when you go from a neutral species to a cation, it gets smaller. When you go from a cation to a dication, it gets smaller still. And now we have a charge of 2. So remember I said that the charge to radius ratio for the alkali metal ions was quite low. The charge to radius ratio for the alkaline earth metals is much higher because they're that bit smaller in the same period and they've now got 2+ charge. And what that translates into is very strong inter-ionic interactions. The coulombic forces between these ions are very, very strong. That means that the lattice energies are very, very high. And if the lattice energies are very high, you have very high melting points for the salts, but you also have very low solubility for these species. Because in order to dissolve something, you have to break up the ionic lattice, and it's very difficult to break up these ionic lattices because the coulombic interactions are so strong. So alkaline earth salts, unlike alkali metal salts, and this is a very important distinction, are really quite poorly soluble. So what are the consequences of that? Well, the consequences of that is that we find these things occurring in what we would recognise as being solid materials. So we don't see them so much in seawater like we'd expect to see the alkali metals or as the ions in our blood plasma. We see them in solid type materials. Group trends. Well, the second period elements are actually often a little bit anomalous when we're talking about the general pattern of chemistry of the group. So what I'm saying there is that beryllium is not that representative of all of group 2 chemistry. If you want an element that is representative of group 2 chemistry, then choose magnesium or choose calcium. Now, if we move to the more friendly group 2 metals, magnesium through to barium, of course what's happening there is the ionization potential is decreasing because we're moving further away from the nucleus. The hydration energy is decreasing. Why does the hydration energy decrease as you go down the group? Because they get bigger, and because they get bigger, they're actually lower charge to radius ratio, which makes them less Lewis acidic, and they bind water molecules more weakly. So the hydration energy is actually decreasing, and what you also find is the solubility, because hydration energy is decreasing, the energy you get back when you dissolve something is decreasing, then you find that the solubility of these species also decreases. So if you have a large 2+ cation and a large 2- anion like a carbonate or a sulfate, that's a recipe for a really very poorly soluble material indeed. Small ions like beryllium 2+ polarize large anions, and what you get then is a species that is not very stable. Remember, one of the general points when you're predicting the stability of an ionic lattice is you need to have a match between the size of the anions and the size of the cations. So the most stable lattices are those when the anions and the cations are matched fairly closely in size.